Okay, so we have had 4 classes so far. Okay, and in those 4 classes, the topics we have talked about are well, started with a brief history of quantum mechanics, vectors, vector spaces, etc. So I hope that these concepts of, and then the main thing is that we, in complex vector spaces, is the concept of Bras and Ketz and Hermitian adjoint. And what else? Okay. And orthogonality of vectors, inner product, reality of inner product, then Stern-Gerlach experiment, and how it shows us that electrons have 2 spin states, up and down states. So we associate the state of a electron with a 2-dimensional vector space, a 2-dimensional Hilbert space. And we refer to those 2 states as our up state and our down state. If you want, we can also call them the 0 state and the 1 state, or you can call them anything you want. It doesn't matter. The point is it's a 2-dimensional vector space. That's all the only thing that really matters. So then I talked about, well, what does it mean that, what do these coefficients mean? What do they tell us? And the answer is that they give us the probability of measurement of either one of the states. So if instead of an electron, you think of a coin, and you have a coin and you toss it, and there are two sides of the coin, heads and tails, and so you can get either heads or tails. But the probability for both of these has to always be always has to add up to 1, right? And what are these probabilities given by? They are given by the alpha squared and beta squared, right? The modulus squared of the coefficients. So that is what this alpha and beta, they represent physically, right? And so normalization of probability implies that alpha square plus beta square has to be 1, right? Then I talked about how to take an inner product. Again, if you are, if this seems odd, if this seems strange to you, this inner product between Bras and Ketz, you can just instead work with ordinary real vectors with which you are comfortable. And I gave you an example of 2 vectors taking the inner product, and that inner product works out in exactly the same way. So the only difference is that for our complex vector spaces, our inner product is asymmetric, meaning that A dot B for a real vector space, A dot B is equal to B dot A. But for a complex vector space, H, inner product of H with T, is not the same as the inner product of T with H, right? They are related to each other. How are they related to each other? So the inner product of 2 states. So if I have 2 states, psi and phi, if I take the inner product of these 2, then this, how is this related to, how are these 2 numbers related to each other? This is the complex conjugate of the other one. This also tells us that if you take the inner product of a vector with itself, then by definition, this has to be a real number by the fact that it is equal to its own complex conjugate. Okay. So now, in any questions at this point?
No, sir.
Okay. All right. Okay. So let's see. What are the things we have talked about? We talked about vectors, Hilbert space, We've talked about measurement and measurement and probability. And in this measurement process, it is important to remember the role of this collapse. So this collapse process is very important. And we don't have a complete understanding of what this collapse is or how it occurs, but we know it happens. Okay. So what is the collapse? Collapse is that you have a state psi, and you can write it as a superposition of some basis states. So let's say your Hilbert space has some basis states phi I. So okay, so these states phi of I, with I goes from 1 to n. So n is the dimensionality of your Hilbert space. Then what you have is, so when this state collapses, what happens is that in a measurement, all of the coefficients become 0 except for one coefficient, right? Now you don't know which coefficient that is going to be until you take that measurement. Which state that it collapses into, you don't know. Okay. So this collapse, what is it? It's basically a projection. If you imagine that you have a many dimensional Hilbert space, okay? Now on paper, I cannot draw orthogonal vectors for more than 3 dimensions. So I'm just drawing these vectors like this, okay? These are all supposed to be basis vectors, and they're all supposed to be perpendicular to each other, okay? So 1, 2, 3, 4, 5, these are all perpendicular to each other, all right? This is just a schematic drawing. And you have some vector in this space, which is a superposition of these vectors. So it has some component along the 3 direction. It has some component along the 2 direction. It has some component along the 1 direction. It has some component along the 4 direction, right? And so on and so forth. So what happens is that the collapse process, it randomly picks out one of those components. Okay. So for example, if this is a 5-dimensional Hilbert space, it will have 5 components: psi 2, psi 3, psi 4, and psi 5, right? And so which one of these will be picked out, we don't know. Okay, so this is important to understand. So now the thing is that how do you when we take a measurement, right, we have to ask what is the measurement of, right? So how to measure specific quantities, right, or characteristics of a system? What are the properties of a system that we can measure, and how do we measure them? So as an example, we'll again look at our Hilbert space for a spin 1/2 particle. Okay, and we will ask the question, what is it that we can measure? So in this case, there is really only one thing that we can measure, right? The only measurable quantity, so also known as an observable, something that you can observe, is what? It's the angular momentum. Right? And what is the angular momentum? And the angular momentum is simply, there are only 2 possibilities. there is either plus h bar by 2 or minus h bar by 2, right? And plus h bar by 2 corresponds to the up state and minus h bar by 2 corresponds to the down state. So now the question is, how do I represent this mathematically? Okay. So for this purpose, now we introduce operators, right? So we have a vector space, right? What is a vector space? A vector space is the states, which are the vectors, but the vectors themselves have no meaning unless and until you can transform those states from one, you can go from one state to another state. Until and unless you can go from one state to another state, right? How will you describe any kind of dynamics in the system, right? So how should this transformation happen? Well, what is phi? Phi is an element of our Hilbert space, vector space. Psi is also a vector. So if I want to take one vector, an element of V, into another element of V, right? What is the simplest way in which I can do that? Anybody? Anybody? How do I take one vector into another vector? So, okay, so let me write down a vector V in terms of its indices, okay? V1, V2, Vn. And I'll write down another vector U as U1, U2, Un. And I want to take the vector U and transform it into the vector V, right? So that means my components of the vector V. So V has, let's say, n components. Let me take the ith component, okay, V of I. V of I will be some function of my U components of U, right? Yes?
Yes, sir.
Okay. Now, so, and this function also will depend on I, right? So there will be n functions, one for each component of V. Now, in general, right, these functions f of I are arbitrary, right, in general. Meaning, so for instance, one could have some sort of non-linear function. One could have, in the case of two component vectors, again, one could have V1 is equal to cosine U1 plus U2, something like this. V2 is equal to sine U1 plus U2, right? But there is a problem with using such functions. What is that problem? What is the fundamental characteristic of vector spaces? They are linear, right? Linearity is the fundamental property of vector spaces, right? So if you use functions like this, these are non-linear functions, right? So what is the meaning of linearity? Linearity means if I take my vector U and multiply it by some number alpha, then my function of U becomes f of u alpha u, and this should be equal to alpha of fu. This is the meaning of linearity. If this property is not satisfied, then my function cannot be linear. Okay. And if u itself is equal to the sum of some other two vectors, let's say I have two other u, v, w, x, y, let me use x and y. Let's say I have two other vectors x and y. What is the meaning of linearity? A linear function of u should have this property, right? F of u is equal to f of ax plus by, and if it's a linear function, it should act like this. Right? This is linearity. Right? So if I look at functions like this, are they linear? They are not linear, because if I take u to alpha u, what happens to the cosine functions? That example I gave you, cosine of alpha u1 plus alpha u2, right? This is not equal to alpha times cosine u1 plus u2, right? And it's also not equal to alpha cosine u1 plus alpha cosine u2, right? It is not linear in its arguments. Okay. I forgot to share the YouTube link with you all, but I mean, I think that since it's on my channel, Dheeraj is already watching. So if you are on the channel, you will obviously see the live stream without the need for the link. Okay. So what we want is a way to transform of vectors into each other using functions which are linear. Okay. Now, what are the simplest linear functions? The simplest linear function is just this. This is a linear function. Right? It is a linear combination of the components. Right? So we can write this in this form. Right? So what is this? This is now this expression is a matrix expression. Right? We can collect these coefficients A, B, C, D into this object, that is, and we call that object a matrix. Right? And see, one of the beautiful things is that you have to realize that whoever decided that we can go from this expression to this expression, right? This is a huge jump in itself. See, for us, it is obvious. We have been working with these since we were babies, or well, relatively babies. But at that point in time, somebody would have said, well, what the hell is A? Why does it have its own independent existence? Right? But A does have its own independent existence. Right? For example, you can have a matrix which is the inverse of A. What is the property of the inverse of A? The product of the A with itself will give you the identity matrix. So if you take the inverse of A and multiply both sides of this equation from the left, what will you get? You will get, this will be the identity, and you will get U is equal to A inverse B, right? So these two, this is how do you go from V to U? From U to V, you multiply by A. How do you go from V to U? You multiply by A inverse, right?
Yes, sir.
Yes, sir.
So we have two vectors, U and V. To go in this direction, we multiply by A. To go in this direction, we multiply by A inverse. Okay. My vectors are not drawn very well. Okay. And what is this A? This A is what we refer to as an operator. Okay. Now, technically, any function, even this function is also an operator. Okay. Anything which an operator is basically a machine. Okay. It has some inputs and it has some outputs. That's an operator. It takes in some inputs and gives you some outputs, right? In our case, the number of inputs is equal to the number of outputs, and we want the operation to be linear. So if we want to have a linear operator, right? So in general, what I can say is V is equal to the some operator acting on U, right? O is some operator, some machine which is taking in components of U and giving me components of V. And I require that O should be linear. That means that if U is equal to AX plus BY and I take O of U, if O is linear, I should be able to write this as A times O of X plus B times O of Y. Okay. And this condition, if I impose this condition, then linearity implies that O must be a matrix. Okay. So all linear operators have this form. All linear operators are like matrix, can be written as a matrix. Okay. So why did we start talking about operators? Because I wanted to talk about how to measure something, and we want to measure something, which in this case, that something is the angular momentum of the system. Okay. So returning to spin 1/2. Okay. Now we want to measure the angular momentum. So this is a postulate of quantum mechanics that any observable is associated to a operator. Okay. So as an example, so this is a postulate of quantum mechanics. Okay. So one of the postulates of quantum mechanics is that vectors are equal to states. State of a quantum system is given by a vector in a Hilbert space. That is one postulate. This is second postulate. Okay. And there is a little more detail that I'm leaving out. I'll come to that in a little bit. Okay. So as an example of this, as an example of an observable or an operator, let me consider something called sigma z. Okay. Sigma z is a matrix which has these components. Okay. Now, whenever I have an operator, okay, an operator is a matrix. So if a matrix acts on a state and a state is a vector, then I can have an equation of this form, right? Where lambda is a complex number, right? What is this equation called? This is called a eigenvalue equation, right? Lambda is the characteristic number, a characteristic value of the operator O, right? Now, if you have a n-dimensional vector, then your operators, your matrices are n by m dimensional matrices, right? So each operator or any matrix can have how many eigenvalues?
And n eigenvalues.
It can have n eigenvalues. Okay. So in this case, for example, I ask what are the eigenvalues of this matrix sigma z. So let's try to figure that out. So we want to solve this expression. We want to solve this equation. Okay. So let us write this equation out in more detail. 1, 0, 0, minus 1, alpha, beta, right? Psi is what? Psi is a vector, right? It has components alpha and beta. Is that fine? And this is equal to
Yes.
lambda times alpha, beta. Right? Now to solve this, we'll use a small trick that if I have some number times psi, that can also be written as number times the identity matrix times psi. Okay. Why? Because identity matrix times psi is equal to psi, right? And then this can be written as lambda times the identity matrix times psi. Okay. And what do you get when you take the identity matrix and multiply by a scalar? You get this matrix multiplied by alpha, beta. Okay. So what do you get from this expression? 1, 0, 0, minus 1 times alpha, beta. And on the right side, we can write lambda 0 0 lambda alpha beta. Okay. Any questions so far?
No, sir.
Okay. So now we can solve this equation. Okay. How do we solve this equation? We can take both of the expressions onto one side. Now this is a matrix. This is also a matrix lambda I. So the whole thing can be written as a one equation. Right? I can take this matrix over to the left hand side, and so then this becomes the first matrix minus the second matrix times the vector psi is equal to 0. Right? And what is that? That is 1 minus lambda 0 0 minus 1 minus lambda 0 times alpha beta is equal to 0. This is now our, right? This is what we are left with. And now whenever you have the situation that some matrix multiplied by some vector one second, huh? Okay. So whenever you have this condition that your matrix multiplied by some vector is 0, okay, and V is non-trivial, meaning V is not 0, right? Meaning the components of V, so in this case alpha beta are not 0. Then that determinant of M has to be equal to 0. For this equation to have a solution, determinant of M has to be equal to 0. Okay. You can show this. This is a very basic step in linear algebra, right? That if I take any matrix, let's say A1, and then I take that matrix and multiply it by any vector. So I get A11 V1, A12 V2, A1n Vn is equal to 0. This is one equation. Right? So let's say you have some matrix expression like this. Then this matrix expression becomes equal to this, is the same as this set of linear equations, right? And how do you solve these linear equations? You solve this system of n linear equations by eliminating each one of the variables, right? So for example, I will take these two equations. I'll multiply the first one by A21 and the second one by A11. And then I can subtract these two equations, right? When I subtract these two equations after multiplying by A11 and A21 here, what will happen? This term will cancel out. Right? I'll be left with one equation with n minus 1 unknowns. So you keep repeating this process, right? And at the end of the day, what you will be left with when you keep multiplying and subtracting and multiplying by subtracting, you'll be left with a quantity which is basically the determinant of the matrix A. Right? You can see this for the case of a two-dimensional equation. So if you are in 2 dimensions, right? Alpha and beta are your unknowns. So your linear equations become this, right? And now you multiply this by C and multiply this by A, and then you subtract, right? What do you get? The first term will cancel out. The second term will be BC minus AD times beta, right, is equal to 0. This is what you will be left with, right? Now we have already assumed that beta is not equal to 0, right? If beta is equal to 0, then we have a degenerate solution. We have a trivial solution. So if beta is not equal to 0, then BC minus AD is equal to 0. What is this? This is equal to the determinant of this matrix. It's the negative of the determinant, but it doesn't really matter, right? So when you do all this procedure, you find that the determinant of A has to be 0 for a non-trivial solution to this expression, right? AV is equal to 0. So this is all linear algebra, which technically, I mean, you should all know, but that's I'm just covering it just to make sure that you all understand what's going on. Okay. So coming back to this expression, now we have this equation, right? And so now we can see that for this equation to have a non-trivial solution, we require the det of A minus lambda I has to be equal to 0. If the determinant is not 0, then you will not have a non-trivial solution. Then what is this determinant? Well, what is this matrix? Matrix is, in our case, it's 1 minus lambda, 0, 0, minus 1 minus lambda. What is the determinant of this? It's just this times this. So that's minus, and then 1 minus lambda squared, right? And this has to be equal to 0. This gives us two solutions for lambda. Lambda is equal to plus or minus 1. These are the eigenvalues. Right? So we have solved our eigenvalue equation. What was our eigenvalue equation to begin with? It was this expression, right? And now we know what are the possible values of lambda. The possible values of lambda are plus 1 and minus 1. So we have our eigenvalues. What about our eigenvectors? We don't know what our eigenvectors are, but we can easily guess them now, right? We have an eigenvector for lambda is equal to plus 1. And that means that if I take this matrix multiply by alpha beta, I should get lambda is equal to plus 1. That means this will be just plus 1 over here, and I should get alpha beta, right? Now, what is the possible solution of this? Possible solution is that, well, alpha can be arbitrary. Okay, alpha can be anything, and beta is equal to 0. Right? So if I have alpha 0, then 1, 0, 0 minus 1, what will this give me? This will give me alpha 0. Similarly, if I take 1, 0, 0 minus 1 and 0 beta, what will that give me? It will give me minus 0 times beta. Right? So this corresponds to lambda is equal to plus 1. This corresponds to lambda is equal to minus 1. Right? Now you will say, well, these are not unique eigenvectors. So they are unique up to scaling. Right? So this I can write as alpha times 1, 0. And this I can write as beta times 0, 1. So what are my eigenvectors now? My eigenvectors are the up state, which is 1, 0, and my down state, which is 0, 1. These are my normalized eigenvectors. Right? So if I take this eigenvector and normalize it, I will get this guy. And okay. So this corresponds to lambda is equal to plus 1, and this corresponds to lambda is equal to minus 1. Okay. Now, finally, we can come to the statement of measuring of angular momentum. And remember, this is along the z-axis. Okay. And again, I put the z-axis in quotes because the z-axis is something that we have freedom to define. We can pick any axis as our z-axis. So the angular momentum operator, let me call it S of z, is equal to h bar by 2 times sigma z. Okay. And this operator will have two eigenvalues. Those eigenvalues are plus h bar by 2 and minus h bar by 2. Right? It's just plus 1 multiplied by h bar by 2 because this is just scaled up by that factor. Okay. All right. So now we can talk about what these measurable, what is the meaning of this measurement process? How are we performing a measurement? So when we say we are performing a measurement, we have some operator. And when we perform that measurement, what happens is that operator has some eigenstates. Okay. So these are the steps in measurement. First of all, you have an operator. There is another property. We require that these operators should be Hermitian. Okay, I'll talk about that later. We have some operator. We have some set of eigenstates of that operator. Okay. What happens after measurement is collapse happens. Collapse. What does the state collapse into? the state collapses into one of the eigenstates of this operator. And what is the result of the measurement? The result of the measurement is the associated eigenvalue. Okay. So I'll leave it here for now. In the next class, we'll talk about expectation values and other things. And we'll talk about uncertainty in measurement. How do we define uncertainty in terms of operators? We'll talk about commutation, commutators and anti-commutators. What are those things? And simultaneous measurements. Okay. But this is the basic process of measurement. So what happens when I measure this spin operator? The system collapses into either this state or this state, right? So to begin with, the system was in a superposition of these two states just before the measurement happened. Okay. After the measurement, what happens is it collapses into either the up state or the down state. And there is a probability. What is that probability? The up state probability is alpha squared and down state probability is beta squared. Okay. And this probability is a statistical statement, right? So you can't do this experiment once and get alpha and beta. The statement is that when you do the experiment an infinite number of times, technically, or n number of times, where n is a very large number, then in the limit that n goes to infinity, and again, assuming you start from the same state every time, what will happen out of those n numbers, right? Alpha square is a number, alpha square and beta square add up to 1, right? So these are both fractions. So alpha square times n times, that is the number of times you will get up or heads, and beta square times n is the number of times you will get down or tails. But these are statistical statements. So it doesn't mean that, for example, let's say that alpha and beta are equal. Okay, let's say you set them both to be equal to 1 by root 2. Why 1 by root 2? Because 1 by root 2 square is 1/2, 1/2 plus 1/2 is 1. So if they are both equal to 1 by root 2, and let's say that you conduct the experiment once and you get the up state, does this mean that in the next time you will get the down state? And the answer to that is no, because this is a statistical statement. It applies only in the limit of large numbers, repeating this experiment many times. Okay.
Yes, sir.
So this is the statement of now. Okay, questions. Questions. Let's see. Questions on YouTube? No questions on YouTube. Questions in Telegram? No questions. Okay, so I'm going to stop the YouTube live streaming and the recording.